Let me contrast the iterative procedure, just so you see where space does build up, with the recursive procedure, so you can see the difference. Let's look at the evaluation of recursive factorial. All right, so here's fact recursive, or standard factorial definition. We said this one is still a recursive procedure, but this is actually a recursive process. And then just to link it back to the way we started, we said, oh, you can see that it's going to be a recursive process by the substitution model, because if I say recursive factorial of 5, that turns into 5 times, what's it, fact rec or rec fact? 5 times recursive factorial of 4, which turns into 5 times 4 times fact rec of 3, which returns into 5 times 4 times 3 times, right, and so on. Right? The idea that there's this chain of stuff building up, which justified in the substitution model the fact that it's recursive. And now let's actually see that chain of stuff build up and where it is in the machine. Okay. All right, well, let's imagine we're going to start out again. We'll tell it to evaluate recursive factorial of 5 in some environment, again, E0, where recursive factorial is defined. Okay. Well, now we know what's eventually going to happen. Right? This is going to come along. It'll evaluate those things, figure out it's a procedure, build somewhere over here an environment E1, which has n down to 5, which hangs off of E0, which would be presumably the definition environment of recursive factorial. Okay. And in this environment, it's going to go off and evaluate the body. So again, the evaluation here will reduce to evaluating the body in E1. That's going to look at an if, and I won't go through the details of if. It'll look at the predicate. It'll decide it eventually has to evaluate the alternative. So this whole thing, again, will reduce to the alternative of recursive factorial, the alternative clause, which says this whole thing reduces to times n of recursive factorial of n minus 1 in the environment E1. Okay, so the original expression now is going to reduce to evaluating that expression. Right? Now we have an application. We did an application before. Remember what happens in an application. The first thing you do is you go off and you save the value of the continue register on the stack. So the stack here is going to have done in it. And then you're going to set up to evaluate the subparts. Okay, so here we go off to evaluate the subparts. First thing we're going to do is evaluate the operator. What happens when we evaluate an operator? Well, we arrange things so that the operator ends up in the expression register, the environment's in the end register, continues someplace where we're going to go evaluate the arguments, and on the stack we've saved the original continue, which is where we wanted to be when we're all done, and then the things we needed when we're going to get done evaluating the operator, the things we'll need to evaluate the arguments, namely the environment and those arguments, those unevaluated arguments. So there they are sitting on the stack, and we're about to go off to evaluate the operator. Okay. Well, when we return from this particular call, so we're about to call eval dispatch here. When we return from this call, the value of that operator, which in this case is going to be the primitive multiply procedure, will end up in the fun register. We're going to evaluate some arguments. Say we'll evaluate n here. That'll give us 5 in this case. We're going to put that in the argle register, and then we'll go off to evaluate the second operand. So at the point where we go off to evaluate the second operand, and I'll skip details like computing n minus 1 and all of that, but when we go off to evaluate the second operand, that will eventually reduce to another call to fact recursive. And what we've got on the stack here is the operator from that combination that we're going to use it in, and the other argument. Okay, so now we're set up for another call to recursive factorial. And when we're done with this one, we're going to go to accumulate the last arg. And remember what that'll do. That'll say, oh, whatever the result of this has to get combined with that, and we're going to multiply them. But notice now, we're at another recursive factorial. We're about to call eval dispatch again, except we haven't really reduced it because there's stuff on the stack now. Stuff on the stack says, oh, when you get back, you better multiply it by the 5 you had hanging there. So when we go off to make another call, we evaluate the n minus 1. That gives us another environment in which the new n is going to be down to 4, and we're about to call eval dispatch again. Right. We get another call. That 4 is going to end up in the same situation. We'll end up with another call to fact recursive n, and sitting on the stack will be the stuff from the original one, and now the subsidiary one we're doing. And both of them are waiting for the same thing. They're going to go to accumulate a last argument. And then, of course, when we go to the fourth call, the same thing happens. Right? And this goes on and on and on. And what you see here on the stack, right, exactly what's sitting here on the stack, the thing that says times and 5, and what you're going to do with that is accumulate that into a last argument. That's exactly this. Right? This is exactly where that stuff is hanging. Effectively, the operator you're going to apply, the other argument that it's got to be multiplied by when you get back, and sort of the parentheses which says, yeah, what you wanted to do is accumulate them. So you see, the substitution model is not such a lie. That really is, in some sense, what's sitting right on the stack. Okay. All right, so that's the difference. That, in some sense, should explain for you, or at least convince you, that somehow this evaluator is managing to take these procedures and execute some of them iteratively and some of them recursively. Even though, as syntactically they look like recursive procedures, how's it managing to do that? Well, the basic reason it's managing to do that is the evaluator is set up to save only what it needs later. So, for example, at the point where you've reduced evaluating an expression and an environment to applying a procedure to some arguments, it doesn't need that original environment anymore, because any environment stuff will be packaged inside the procedures where the application is going to happen. Right? Similarly, when you're going along evaluating an argument list, when you're finished evaluating the last argument, you don't need that argument list anymore. Right? And you don't need the environment where those arguments would be evaluated. Okay? So the basic reason that this interpreter is being so smart is that it's not being smart at all. It's being stupid. It's just saying, I'm only going to save what I really need. Well, let me show you here. Here's the actual thing that's making a tail recursive. Remember, it's the restore of continue. It's saying, when I go off to evaluate the procedure body, I should tell eval to come back to the place where that original evaluation was supposed to come back to. So in some sense, if you want to say what's the actual line that makes a tail recursive, it's that one. If I wanted to build a non-tail recursive evaluator for some strange reason, all I would need to do is, instead of restoring continue at this point, I'd set up a label down here called where to come back after you finished applying the procedure. I'd set continue to that. I'd go to eval dispatch, and then eval dispatch would come back here. At that point, I would restore continue and go to the original one. So here, the only consequence of that would be to make it non-tail recursive. It would give you exactly the same answers, except if you did that, iterative factorial and all those iterative procedures would execute recursively. Okay. Well, I lied to you a little bit, but just a little bit, because I showed you a slightly oversimplified evaluator, where it assumes that each procedure body has only one expression. Remember, in general, a procedure has a sequence of expressions in it. So there's nothing really conceptually new. Let me just show you the actual evaluator that handles sequences of expressions. This is compound apply now, and the only difference with the old one is that instead of going off to eval directly, it takes the whole body of the procedure, which in this case is a sequence of expressions, and goes off to eval sequence. And eval sequence is a little loop that basically does these evaluations one at a time. So it does an evaluation, says, oh, when I come back, I better come back here to do the next one. And when I'm all done, when I want to look at the last expression, I just restore my continue and go off to eval dispatch. And again, if you wanted for some reason to break tail recursion in this evaluator, all you need to do is not handle the last expression specially. Just say, after you've done the last expression, come back to some other place, after which you restore continue. And for some reason, a lot of Lisp evaluators tended to work that way. And the only consequence of that is that iterative procedures built up stack. And it's not clear why that happened. All right, well, let me just sort of summarize, since this was a lot of details in a big program. But the main point is that it's no different conceptually from translating any other program. And the main idea is that we have this universal evaluator program, the metacircular evaluator. If we translate that into Lisp, then we have all of Lisp. And that's all we did. The second point is that the magic's gone away. There should be no more magic in this whole system, right? In principle, should all be very clear, except maybe for how Lisp structured memory works. And we'll see that later. But that's not very hard. The third point is that all this tail recursion came from the discipline of eval being very careful to save only what it needs next time. It's not some arbitrary thing where we're saying, well, whenever we call a subroutine, we'll save all the registers in the world and come back. Right? See, sometimes it pays to really worry about efficiency. And when you're down in the guts of your evaluator machine, it really pays to think about things like that, because it makes big consequences. Well, I hope what this has done is really made the evaluator seem concrete. Right? I hope you really believe that somebody could hold a Lisp evaluator in the palm of their hand. Maybe to help you believe that, here's a Lisp evaluator that I'm holding in the palm of my hand. Right? And this is a chip which is actually quite a bit more complicated than the evaluator I showed you. Here's a better picture of it. What there is you can see the same overall structure. This is a register array. These are the data paths. Here's a finite state controller. And again, finite state. Right? That's all there is. And somewhere there's external memory that'll worry about things. And this particular one is very complicated because it's trying to run Lisp fast. And it has some very, very fast parallel operations in there, like if you want to index into an array, simultaneously check that the index is an integer, check that it doesn't exceed the array bounds, and go off and do the memory access, and do all those things simultaneously. And then later, if they're all okay, actually get the value there. So there are a lot of complicated operations in these data paths for making Lisp run in parallel. It's a completely sort of a non-risk philosophy of evaluating Lisp. And then this microcode is pretty complicated. Let's see, there's about 389 instructions of 220-bit microcode sitting here, because because these are very complicated data paths, and the whole thing has about 89,000 transistors. Okay. Okay, well, I hope that sort of takes away a lot of the mystery. Maybe somebody wants to look at this. Yeah. Okay, let's stop.
It sounds like what you're saying is that with the restore continue put in the proper place, that procedures that would invoke a recursive process now invoke an iterative process, just by the way that the eval sequence works?
I think the way I prefer to put it is that with restore continue put in the wrong place, you can cause any syntactically looking recursive procedure, in fact, to build up stack as it runs. But there's no reason for that. So you might want to play around with it. It's just, you can just switch around 2 or 3 instructions and in the way compound apply comes back, and you'll get something which isn't tail recursive. But the thing I wanted to emphasize is there's no magic. It's not as if there's some very clever pre-processing program that's looking at this procedure, factorial iter, and say, oh, gee, I really notice that I don't have to push stack in order to do this. Some people think that that's what's going on. It's something much, much more dumb than that. It's this one place you're putting the restore instruction. It's just automatic.
Okay.
Yeah.
But that's not affecting the time complexity, is it?
No.
It's just that it's handling it recursively instead of iteratively, but in terms of the order of time it takes to finish the operation, it's the same one way or the other, right?
Yes, tail recursion is not going to change the time complexity of anything, because in some sense it's the same algorithm that's going on. What it's doing is really making this thing run as an iteration, right? Not going to run out of memory, counting up to a giant number, simply because the stack would get pushed. See, the thing you really have to believe is that when we write, we've been writing all these things called iterations, infinite loops, like, right, define loop to be call loop. That is as much an iteration, as if we wrote do forever loop. Right? It's just syntactic sugar is the difference. These things are real, honest-to-God iterations. Right? They don't change the time complexity, but they turn them into real iterations. All right, thank you.